let's talk about adhesion, cohesion, and surface tension. So this is an introductory video, and I'll put an extended video as well for surface tension to maybe give some more insight. I'll put a link up above there once it's up. Now, let's start with just adhesion and cohesion. Let's break those down and then tie it into surface tension. And this is for liquids, although adhesion and cohesion doesn't necessarily have to be thought about in terms of liquids. Now, for adhesion and cohesion, so what's the difference between those? And here I want to be able to kind of refer to the forces, so adhesive forces and cohesive forces that are keeping kind of materials together. Now, when we use the term adhesion, so that is in this particular term, we are referring to when two objects of a different kind, okay, are basically in contact with each other in some way, and then there is some forces which are keeping them together. You can almost think of it as if you take one object that you have, and then, you know, if you stick glue on top of it, so the glue will actually adhere to the other object, but yet they're two separate kind of entities. And, you know, visually, so what you can think about is if you do have one object, so let's say we have this big object, and then we have a smaller object. And now if I take the smaller object, you know, and let's say, you know, if I attach it, now if I put it on top, may not be adhesive forces, might just be gravity working. But if I put it on the side, right, and it sticks to it and it doesn't actually kind of fall, so it just kind of adheres to the object, yet the two objects are completely different. So again, you can think about glues, we certainly use those. You can think about tape as well, so adhesive. Okay, so those are adhesive forces that are keeping two things that are different from each other together. Now, cohesive forces, so what's interesting is that cohesive forces do the same thing. So they keep things together, but they keep things together of the same kind. So here, you know, you would concentrate only, okay, on one item. So if I now remove this item entirely, so let's concentrate just on this item on its own. So now this particular item, and let's think about liquids because I want to be diving into surface tension from these cohesive forces. Well, so any liquid, okay, has a certain amount of particles. Now I'm going to refer to particles, so not just like molecules or atoms. I'm just going to call all of it just kind of a particle. And then there is interconnective kind of forces in between them. Now, you don't have to understand the details, okay, of those forces, but you can imagine that if you do take an object and you start breaking it down, you kind of start zooming in. So I'm going to try to do that here. So if we take the same object and then we start zooming in here, okay, you're going to see that, you know, you're going to have these particles, okay? They may not be necessarily nicely aligned as I have them in here. And what I want to talk about first in terms of cohesive forces is the fact that if you do have a liquid, right, so those cohesive forces are the forces that are acting so that those particles don't start to escape and they don't become a gas, so they don't start to evaporate. So something is holding them in together so that it can stay as a liquid. Now, of course, that particular liquid, so as you know, if you pour it into a container, it will take the shape of a container. But still, okay, in between those, there's enough cohesive forces that are keeping them in that sure, they might fill the container, but they're still not evaporating out. So, let's think about this now and try to talk about the extension to surface tension, right? And then what is this surface tension? So the word tension you maybe have heard of, right? So that has something to do with forces. And now in the fact of cohesive forces, so those are the kind of inter forces that are acting within the same object or within the same kind. So maybe you can think about water, right? So those are the things that are keeping the water molecules together and they're not allowing them to escape. Now, of course, sometimes one of them might escape, but for most part, right, depending on the temperature, they'll kind of keep them together. So those are the cohesive forces. And the adhesive forces, remember, were between two separate things. But now when you're talking about the kind of interior molecules of the same kind, so those are cohesive. So when I ever say now cohesion, that's what I am referring to. So cohesion are the actual forces that are keeping these things in. So now diving into surface tension. So let's break this down, and maybe what I'll do is, let's take this kind of the vertical component. So, kind of up and down, so this is going to be made up of many different particles that are lined up, okay, kind of like this. And of course they span out. So I'm just looking at the up and down. So that up and down, I'm going to try to capture over here. So we have, one particle over here, we have another particle and another particle and so on. Now, these particular particles, so let's concentrate the ones that are kind of below the surface, right? So these are kind of on the surface right here. So I'm going to kind of circle this in. So those are the surface ones that I have. But now the ones that are within the surface, so it doesn't matter where they are, but somewhere below, what you will have is that the cohesive forces, right? So you're going to have all of these different forces, okay, that are interconnecting in between the actual molecules. And those cohesive forces, because you're kind of in the middle and you're surrounded all the way by particles. So this one particular particle doesn't really have an overwhelming cohesive force that tries to pull it in any direction. It more or less is balanced off between the forces around it. So that happens, okay, below the surface. So those particular particles below the surface are just kind of acting within these cohesive forces that they have, and they kind of stay within there. Sure, they're kind of rolling around because it depends, maybe there's current in the water or something, but we're thinking about kind of still water, okay? So think about still water, nothing really moving. So those would be the cohesive forces. Now, if you get to the surface, now all of a sudden, so sure, you do have these cohesive forces, but these cohesive forces, what they're trying to do is, they're trying to take these molecules, okay, because they're exposed to the top. So they're basically, let's imagine it's air or some gas. That gas that it has right here, so up above it, it doesn't have enough kind of energy and enough forces to kind of pull these away. Now sometimes, rarely it does happen because we know water, for example, will evaporate slowly over time. But kind of if you take the time frame and make it a lot shorter, these particular particles are not really going to be escaping out, because if that was happening, then eventually these ones would escape as well. So those would be kind of like, evaporation as a whole. But now we're just kind of stuck at the liquid state. But if these cohesive forces are there, right, but we don't have any balancing act coming in from the top, so that means that these kind of in between create this kind of tension in between, where it wants to take the particles on top and kind of suck them back in, right? But if you're going to get sucked back in, so if you're thinking of a volume that you have, then it's going to try to minimize, right, that surface. It's going to try to minimize that surface area as much as possible, because it's trying to take those particles and use the cohesive forces to kind of suck them back in, right? So all of these ones from the bottom are trying to kind of pull these guys back in. And that cohesive force, right, so that force that you have, it creates very much like a surface that you would think about the same thing with solids. So if you take a solid, and that particular solid, if you looked at it, right, if you had almost like the surface that you would have, I'm going to take kind of a napkin to illustrate this. So you can imagine that these are right on top and they're kind of bound together, right? And then there's, you can create tension, right? So I can kind of pull on these and I can create a tension along, but it would be, of course, a tension everywhere around. And that tension is caused because of the fact that these cohesive forces, okay, are pulling it all the way through. And now, as you know, if I have this sheet, I can certainly put something on top of it, right? So I'm going to put this pen, right? I'm going to put it up on top, and it doesn't fall through, okay? But that's because this is a solid, and these cohesive forces that I have within here, okay, are strong enough to withstand that. Now, in a liquid, okay, the surface tension, so the tension, okay, which is created, that you have within there, that tension isn't that strong like you would have on a paper like I just showed you, or on some kind of a solid, right? Obviously it's not that strong, but yet it is there, okay, and it's minuscule. So now if I kind of scroll back up here, and I'm going to just now concentrate and shift back out just on the surface, So let's imagine we're just talking about this surface right here. So, this is like a liquid that you've poured in, and I'm taking it, and this is the entire surface up on top here. Okay, so that's what I would have. So that surface, okay, I'm going to now switch over. So let's imagine that this is the surface that I'm discussing in here. So for this particular surface that I have, okay, so that's right on top. So these particles are right up on top. Well, if you were imagining, okay, that on that surface, because of the cohesive forces, it's acting kind of like this paper. So that means that you could possibly put something on it, right? And yet it wouldn't fall through. Of course, if it doesn't have a big weight. If the weight is too big, it will just tear through, right? It will just go right through and it will fall through the actual liquid and fall inside. But we have, kind of water spiders, which are very tiny. You can take a hair and you can notice that, all of a sudden, it's not necessarily floating. It's actually sitting right on top. Sitting right on top. And what is happening is that these molecules, they will bend, so that you can kind of just bend them out, but this will be sitting in. And it's creating this tension. It's holding in kind of like a rope that you would have. Okay, and if you placed something on top of the road or you hung something on top, it would just be sitting there, right? Unless you would actually break through that surface tension. And for liquids, so it turns out that yes, we do have this tension. It exists. And it's not just on top of the surface as you're thinking about from the vertical side, right? And then coming down. But it also exists from the viewpoint that you can actually have, and you can think about a water droplet, right? A water droplet also has made out of kind of particles. So, I can take one of these and I can think, okay, let's think about this as a water droplet right here. So I'm going to duplicate it, bring it back out. Okay, let's, make it blue for kind of water, okay, within here, and let's maybe make it much bigger. So on the surface there, all the way around, that same cohesive forces are trying to keep these things in. And that's why the water droplet can form. Until, okay, of course, you break through that surface tension. So you can kind of just break through eventually, and maybe the water droplet will scatter through. Okay, so that's something that might happen. You see this also in soap bubbles, right? So if you kind of have these soap bubbles, you'll notice that really you just kind of have air inside, air right outside, but yet this soap bubble is forming because there's some tension holding these particles, molecules together that's strong enough to withstand so it doesn't actually pop. Now, of course, when it pops, the surface tension is broken. Now, when we have these and we talk about the surface tension, okay, when you're talking about liquids, okay, then you can think about if indeed, you have this, and I'm back to the top of the surface, and you wanted to slice through it. So in physics, what we do is, you can take, and you can almost take like a knife, and, you can slice through these and try to see, right? So if I slice through, can I actually break this surface tension and make it fall back in? So how strong is that, right? What's the force there? And notice that, I drew a line, and this is actually how we measure the surface tension. So it's actually the force, okay, which is the stretching force which is permissible before it starts to break, divided by whatever length that you go along. And that is referred to very often as the surface tension. And it is kind of like a coefficient. And depending on what you talk about, if it's water, if it's mercury, blood, okay, or any other liquids that you would have, and this is for liquids, then you can find these values. So, you can kind of search them up on the internet if you like. I don't remember all of them. I'm sorry. I think water is 7.6, times 10 to the negative 2, okay, newtons. And this is again because it's per length. So this would be per meter. So, so the length that I'm referring to is this, right? So it is what stretching force do you need, right, to actually break through that one particular meter so that you can break that tension in the water. And as you can see, it's very tiny. It's not meant to be big because it is a liquid. but yet it is there. And it allows you to keep things together. It allows you to keep things like a drop, which you might think, it's a liquid. Why isn't it just kind of falling through? Because the surface tension around is holding it all in. And it's pretty neat to be able to see that. So this is, I put it in scientific notation. If you put it back in, so this is really, how tiny this is. And we very often just simply write it. So this is a coefficient, and you might see it kind of written like a gamma, like this. And you can look it up, as I said, for various liquids, right? So this is just for water, and I can't remember at what temperature. As the temperature increases for water, this decreases because those particles are moving faster and faster, and then more and more can actually escape, so the surface tension isn't as strong. Right? And it's very simple in terms of its formula, because for any liquid, okay, that you have, so you can put L for liquid, and that would be the force, which is the stretching force that you are allowed to have per the actual length. Okay, so here I have to kind of be careful, because if I put this, I'll put liquid there, and then maybe length, I'll put capital L, but you might see it as a small l as well as a formula. And what this is just saying is, it's just kind of what's the strength that this liquid would have along a particular line, right? So along a particular line, and the force that would be allowed for it to have. So if you take a line, let's say if it was 1 meter, you of course can take this, right, and then rearrange this, and you can say, well, then the stretching force that is allowed is nothing else but the property of the liquid, which is that kind of tension force. So this is the tension force coefficient multiplied by whatever length that you're going along. So you can imagine if you wanted to split these particles through, okay, so what is this length? So that would have been the length from here to here, and then what would have been the actual stretching force, right? And if that stretching force, okay, is less, okay, and it's permissible right here, then it will actually not break through that tension. And that's why you can have a water spider, you can have, hair, which is literally not floating, because floating would kind of be inside there, right? So that would be on buoyant forces, but it's actually just sitting there right on top. It hasn't broken anything through, okay? And those are, you can, again, Google that up, okay? Or actually put it in a search engine to see, let's say a surface water spider, and you can see that it's just literally just sitting, and so it can walk on water. It's so cool, just the way that its properties are, and then it utilizes this surface tension. It's almost like kind of just walking through, as we of course would fall right through because our weight is just way too heavier, okay, and we would break the surface tension, but a water spider can actually just kind of glance through, and it's almost like sometimes you'll see these kind of like jetliners going through these, very quickly hopping on the water. So there you have it. So that's adhesion, cohesion. Cohesion are the forces within, okay, liquids that you have that are keeping it together and keeping that surface bound in, and then you have the surface tension, which we can calculate, and here is the formula. And I'll try to put up an example as a video as well. But this is it for this video. Thanks for watching. See you in a future video. Bye, everybody.